Good evening, ladies and gentlemen. My name is John Bayman. I'm a teacher in the Northern Territory. You have come to listen to Stephen Crouch and Frank Moyer, and hopefully Stephen is live on the phone now. Evening, Stephen.
Good evening, John. How are you going?
I'm very well, and thank you for allowing us to share your screen so early. I do have a nice blurb about Stephen. I do know that he's a talented and passionate mathematician. He relishes the challenge of teaching specialist math to his senior students, both year 11 and 12. And he's always striving to support his students to understand various challenging concepts. He does this by deepening their understanding of the course using the TI-Nspire technology. And I hear you're a bit of a guru on the Nspire. Is that right, Stephen?
I'm not sure about that. I think you're talking about yourself there, but I try my best.
You're a good man. Well, thank you for joining us this evening. And I'm hoping as well that Frank's had a bit better IT issues than me. Frank, are you on the phone now?
I hope so. Can you hear me?
I can hear you very well. I'm hoping other people can. It would be lovely if people in the chat could just add a little few messages, or even in the Q&A window, just to make sure that I can hear you. Again, normally I'm aware of what's going on, but at the moment, thank you. Some of you said all good. So hopefully we're looking good at this end. So Frank has a vast experience in teaching mathematics, curriculum development, and sharing his knowledge at the national and international conferences. Frank is also passionate about rich TAS and the use of CAS to strengthen and deepen students' and teachers' understanding of various mathematical concepts. And I hear, Frank, you've got some very interesting things to share with us this evening.
Hope so.
Good man. Well, thank you. Like I said, please feel free to send in any messages through the chat or the Q&A window. Either myself or Frank or Stephen will endeavour to reply to them. But Stephen, I can see your screen now. I'm sorry we didn't see the photos of you or Frank, but I'll pass over to you and let everyone learn a bit about what you've got to share with us about inverse functions.
No worries. Thank you, John. Excellent. Well, good evening, everyone. Thank you for tuning in tonight. Frank and I have some brilliant stuff to be showing you, especially on how you can use your Nspire CASs to really deepen the conceptual understanding of both inverse and composite functions to your students. So I'll kick tonight's event off with a bit of inverse functions. So the main thing we need to understand about inverse functions is that all we're really doing is swapping y and x. So if you have any relation, a relation is effectively just a collection of ordered pairs. The inverse is just a swap of the x and y, so that we get a new relation with ordered pairs, y and x. That's what we call the inverse. Now, one thing that students need to know is that the original relation, if it is a function, then the inverse may not necessarily be a function. And that is a really key point in the entire concept of inverse functions. So what we need to relate to students is that if a function is one-to-one, then the inverse is also a function, and we denote the inverse function by f to the power of negative 1x. It's also a good idea at this point to tell students that f to the power of negative 1x does not mean 1 over fx, which is in fact the reciprocal of fx, not the inverse. Okay, so we'll start off by doing a very simple example. I've got a function here. Let f have a domain of real numbers, which maps onto all the reals, where fx is equal to 1/5 x cubed minus 2. So a good question we can start off with is saying, is f one-to-one? So that sort of eases into the whole concept of whether an inverse exists or not. And the easiest way to see whether f is one-to-one is to simply graph it. So on page 2.2, I've got a graphing window already set up. So we're going to go back there, and I press the tab button. You can either do that or press Control G as well. So pressing Control G, I'm going to type in the function, which was 1/5 x to the power of 3 minus 2. There you go. That's our general cubic function there. Fortunately, as you can see, the horizontal line test will work. So any horizontal line passing through this function only intersects it once and once only. Therefore, we can say that f is a one-to-one function. Now, in part B, we're going to ask, how can we demonstrate f neg 1x being sketched? So what I've done is I've created a file over here called Inverse Grapher. By the way, all the files that will be shown tonight by both Frank and myself will be available later on in the webinar pack. So feel free to download these files and play with them as you see fit. So I've got a 5 sin x there. I'm just going to change that to the function we have, which is 1/5 x cubed minus 2. Hit enter, and I've modified my fx. Then I move to page 1.2, and here we've got the same graph that I had back in 2.2 on the other document. It's the exact same 1/5 x cubed minus 2. On this file, I can now put the inverse there. As you can see, as I drag the endpoints of fx, you can see the inverse also being generated. What I've done in this file as well is to try and really deepen the conceptual understanding of the concept. I've put sliders here that, number one, show the line y equals x, and number two, actually show the construction of what happens from f of x over to the inverse of fx. So what happens is, as I drag the point on f of x, you can see the reflection of that point in the line y equals x to generate the point on the inverse function. You can do it on either end, and the really cool thing about this feature here is that the orange arrow I've got there shows the actual direction in which it goes as well. So at all these x values, we've got the point on fx transferring across and reflecting to the other side. If I drag this point before the intersection, you can now see it going the other way. Regardless of which way it's going, you can see that the reflection is occurring in the line y equals x. And you can extend the function as much as you want, and you end up with your inverse like that. And the beauty about this file is that you can change this f of x function to whatever you'd like, move to 1.2 and do the same thing. It works for any function you like, as long as of course the function fits within this window. You can also change your window settings if you have any larger functions with larger x and y values. So going back to our function, I've just now demonstrated how f-1x can be sketched. So this would be a good idea to do this when you're introducing the concept of inverse functions. You've explained that inverse functions are basically reflections in the line y equals x. And on top of that, you can then use this file to demonstrate that a bit further. Okay, so what I'm going to do now is actually go ahead and find the inverse function of f. So what we can do is, I'll just quickly go to a calculator page. And in that calculator page, you can do a very easy solve. So menu, algebra, and solve. All we have to do is solve x equals f1 of y for y. So where did I get f1 from? Well, back in our previous graph page, we had f1x defined as our cubic function. So instead of typing out the cubic function over there, you just solve x equals f1 for y, for the variable y, and you end up with y equals 5 times x plus 2, all to the power of 1/3. Of course, when you're writing this down, it's probably easiest to write it as y equals the cube root of 5 bracket x plus 2. That's how you would do it on an exam paper or a SAC paper. One thing to be careful of though, and this is a really good point to tell students, is that when the question says find the inverse function of f, you notice how it doesn't say find the rule for the inverse. So whenever this is stated, you must make sure, or the students must make sure that they actually talk about both the rule of the function, which is y equals cube root 5x plus 2, but they must also include the domain of the function. Now, fortunately, looking back at our inverse grapher, this graph, which is the f of x, the blue one, when it maps onto the graph of the inverse function, the domain of the blue function, the domain of f, is all real numbers. The range of f is also all real numbers. which means that when you map it onto the inverse, the domain of the inverse is the range of the original, and therefore, since the range of the original graph, fx, is all real numbers, the domain of the inverse graph will also be all real numbers. So again, this is a great visual way to demonstrate the concept of inverse and how the domain and range interchange when you're talking about the swapping over of the different domains and ranges. Okay, so moving on to the next question. I've now got a very simple explanation of here. We have f of x being a rectangular hyperbola, which is fx equals 2 over x minus 3 plus 1. Part A says, state the asymptotes of y equals fx. Okay, so we know that the asymptotes of a rectangular hyperbola occur where the denominator is equal to 0, as well as the remaining constant term at the end. To verify that even further, we can just go to a graph page and type that in. So I'll move to a graph page and type in 2 over x minus 3 plus 1. Now, it's not entirely clear where the asymptotes are. So what we can do, just to make it a bit more clearer, is I'm going to go to Menu, Graph Entry, and Relation. So going there, we had an idea that the asymptote, at least the vertical one, will be at x equals 3. I type in x equals 3, and there we go. There's our vertical asymptote at x equals 3. Press the Tab button, and we said that the horizontal asymptote is at y equals 1. So I type in y equals 1, and there we get our horizontal asymptote. Now, if you'd like to make it dashed, as we do when we're drawing it on paper, you can hover over the asymptote, and on the handheld, you press Control Menu. On the computer, of course, you can right-click, but on the handheld, it's Control Menu. So right-clicking that, you can go to Attributes, and move down to the next attribute, and press right arrow twice, and we end up with dash. Likewise, I can do the same thing with the next, Control Menu, and we get Attributes, move down twice to the right, and there we go. Not only that, notice how the calculator has automatically labeled our asymptotes for us. Brilliant stuff. So now that we've got that, we can see that our asymptotes are x equals 3 and y equals 1 for our original f of x equation. Now the question is, what are the asymptotes of y equals the inverse of f? So one way we can do this is, first of all, by actually graphing the inverse function. Now, in case you haven't seen an inverse function being graphed before, the easiest way to do it is to go to Menu, Graph Entry, and Relation. This relation is a really powerful tool, so use it as much as you can. So Menu 3 and 2 to get to Relation, and that gives us the third one because our first two were the asymptotes. The best way to do this is type in x equals f1 of y. So what we've done is we've basically interchanged y and x in y equal fx, and the calculator now draws the inverse for us. So as you can see here, we get another rectangular hyperbola, but this time the x and y asymptotes are actually going to swap. So just to verify that, again, I'm going to press Control G to get the new relation one. And we had x equals 3 as a vertical asymptote. I'm now going to try y equals 3. And what can you see? You can see that the black graph, which is our inverse, certainly has a horizontal asymptote of y equals 3. Again, I'm going to change the attributes to be dashed. We're going to do the same thing again. This time I'll press Tab and use x equals 1 because we had y equals 1 on as a horizontal asymptote of fx. So x equals 1 must be a vertical asymptote of the inverse. Again, I'll quickly change the attributes for that. And there we go. So looking at the black graph, which is y equals the inverse of f, you get asymptotes at y equals 3 and x equals 1. They come from the asymptotes of fx, which were x equals 3 and y equals 1. So again, this is a really good way to show students that asymptotes basically swap over when you find the inverse. So horizontal asymptotes become vertical asymptotes and vice versa. Okay, so now let's move on to another question where we now have to restrict the domain of our function f of x in order to get a one-to-one function and therefore have an inverse exist. So here's our function. It starts at a included all the way to infinity, maps onto r, and our function is fx equals 2 bracket x minus 3 squared plus 1. So that, as we know, is a parabola. So what the first question we're going to ask is, what is the least value of a such that f is 1-to-1? That is, we're asking the question, what is the least value of a such that the inverse exists? So I'm going to go to a calculator. Maybe let's go to a graph page. That might be better. So doc insert graphs. I'm going to type in the function 2 bracket x minus 3 squared plus 1. So there, 2x minus 3 squared plus 1. There is our function. As you can see on this graph, it's clearly not 1-to-1 because any horizontal line, of course, with equation y equals 1 or more, will cross the parabola once or more times. So at y equals 1, it would cross once. At any y value higher than 1, you'd get the horizontal line crossing twice. So it clearly is not a 1-to-1 function. So to answer the question, we need to look back at the original question and see what the domain is. Now we can see that the domain starts at a and goes to infinity. So we need to see that we have our graph sitting like this. We need to restrict the domain at a left point so that it goes all the way to infinity. So I might actually do that in my inverse grapher page, the 2 bracket x minus 3 squared plus 1. So going back to this file over here, we can see that the graph, if you try and draw an inverse for it, it's not going to work. It's not going to get an inverse function because our inverse is now going to be a relation. So using this as an idea, we can then restrict fx to be from any value there. All right, let's try that again. Y equals 2x minus 3 squared plus 1. There we go. There's our parabola. And let's actually find the minimum turning point. So analyze graph, minimum, and our minimum is at 3,1. So what that means is if we restrict our domain, you can restrict your domain by going control equal and then using the given symbol. If we restrict it to be from x greater than or equal to 3, you can now see that the graph is indeed 1-to-1. The horizontal line test will now pass, it works, and we end up with a 1-to-1 function, which means our inverse will exist. So the least value of a, such that f is 1-to-1, that is the inverse exists, is a is equal to 3. Of course, if you want, you can make a equal 4, a equal 5, a equal 6, etc. But the least value, the smallest value that will work, is x equals 3. Or in this case, it's actually a equals 3. So our question then goes along and says, find f neg 1x, find the inverse of x for this value of a. So again, the best way to do that is on a calculator page. So we can go menu, algebra, solve, and x equals f1 of y for y. And you now notice that there's a bit of a problem. Not really a problem, it's that we now get multiple solutions. So you get y equals 2 square root of 2 bracket x minus 1 plus 6 all over 2, and it gives a little domain restriction here. And then there's another solution which is the negative of the other solution. So what we need to be careful of is when you have a problem like this and you get two solutions. Of course, you get two solutions because our original graph was not 1-to-1. So when you're considering which of these two to write down as your inverse function, The easiest way to do it is to have a look at the domain and or range of f of x. So looking back here, we can see that our domain would now start at 3 to infinity. So when the domain of our f of x is 3 to infinity, that means the range of our new graph, which is this one here, all the way back here. There we are. There we go. We want the range of this graph to be 3 to infinity. Now the range of this graph here is indeed 3 to infinity, and the range of the other graph we had on the right-hand side, this one is in fact negative infinity to 3. So I guess one way to do that is to highlight this, and we can copy it, get back on this graph, press Control G, and y equals Control V, paste that in. And as you can see, this new graph, which is our inverse, does indeed have a range of 3 to infinity. If the students are still not convinced, what you can do is then simply graph y equals x. And it's quite clearly seen that when you have y equals x, we have our f of x graph there, we have the inverse graph, and it's quite easily seen that both the graphs are just reflections of each other in the line y equals x. Okay, moving on. Now here's a really interesting problem that you might pose to your students, and that is, what can we restrict the domain of sine of x to be so that we have the inverse existing? Okay, so the thing is with sine of x is that it is a periodic graph. Now, because of its periodicity, y equals sine of x, there we go. The thing with sine of x is because it has a period and it keeps repeating itself, there are in fact infinitely many, you have infinitely many domains that can, infinitely many domains that will lead to a one-to-one restriction on f of x. So with that being the case, if you try and draw the inverse of sine and you do not restrict the domain, you end up with this snaky looking graph that doesn't really make much sense. And it just keeps going on in both directions. So you can challenge the students to think, all right, how can we restrict the domain of this so that our red graph is one-to-one? Of course, you might want to talk about more restrictions, such as what domain can be restricted to, that it's one-to-one and includes the origin as well. So one way you can do that is, of course, use this file and use the blue dots to sort of change the domain via this interactive approach. And what you can see is if you restrict it just so it starts at the minimum and ends at the maximum, you end up with the red graph, which is in fact the inverse sine of x. Now, I understand that this is in fact a specialist mathematics topic, the graphs of inverse circular functions. Nonetheless, it does serve as a good extension for the maths method students, as it really gives them something to work on with restricting domains. And then if they really wanted to take it further, they can go to the next minimum and next maximum, and you can still see that the inverse is also a function. However, that function does not include the origin. So if you want, you can then change that sign to a cos and repeat a similar sort of procedure. And the method students that also do specialists will really be able to benefit from something like this, because when they see it being done, they can truly appreciate the power of the CAS and showing how inverse functions work out. Okay, so I think we can finish off our inverse functions over there. I'll move on to quickly onto composite functions now. I'll probably take just a minute or two so we can move over to Frank and he can show his material. With composite functions,
Stephen.
Yeah.
I was just watching as well, all the colours as well, and the way that it's so interactive, it's so immediate, and the students can really see exactly what's going on, can't they? Like, it's just fantastic. And with the sliders, it really adds another dimension to it.
It really does, yes, exactly right. You're right, John. And the really cool thing with this file is you can play with the function without anything else coming in the way. And then when the students are ready, they can then turn on the inverse, turn on y equals x, and turn on the construction. And that way, they can really see, I guess from a first principle sort of approach, they can see really what the inverse is doing. And the fact that it's so dynamic, like you've said, really helps them remember it even better.
Yeah, that's fantastic. Great work. And like you said, these are all available on the webinar download that will be sent out to participants, but also on the on-demand website as well for TI.
Exactly right, yeah. So all of you watching, please feel free to download it when it's available and play around with it. See if you can add any improvements to it. You can change the colors, you can change the dots, whatever you'd like. But the main thing is that you can tell students they can change that fx to be whatever they like, and sorry, not z squared, x squared, that's better. They can change it to be whatever they like, and then the graph will work on that. So the power of the Nspire is it's very dynamic that way, and they can really play around with the features of it. Okay, so moving on to composite functions. All I really mentioned about composite functions, Frank has a lot more on composite tonight. With composite functions, I guess the best way to explain it to students is that we have a particular function f, which has a domain. So what I'm dragging here is point P, which is a bunch of x values. Those x values go into the function f, and what comes out as an output is an f of x value. So for example here, f of 7 is equal to 5, f of 6 is equal to 2, and f of 3 is equal to 6. So there's a domain of f, which is all these x values. They output into y values, which is the range of f. What then occurs is this range of f then gets input into the domain of g. So the output of the f function becomes the input of the g function. So this is the g of f of x function. So this demonstration here is what g of fx is, or as some of you may know it, GOF, GOF. So an x value goes into the domain of f, an output comes out of it, that output goes into the input of g, and out comes an output of g as well. So this x value goes through many different stages until it gets to the range of GOF. The main idea here, of course, is that if f puts out a number that g of x, there you go. So if f has an input of 3, out comes a value of 5, and let's say g of x is not defined at x equals 5, what happens is that x equals 5 tries to go into g, but g says, no, I do not accept x equals 5. Suddenly what happens is GOF is then undefined at that particular value. So then, of course, you can bring out discussion about when does g of f of x exist, when does f of g of x exist, etc. But I'm sure Frank will talk more about that in his part of the webinar. So John, I'll pass over to Frank. Thanks everyone for tuning in. I hope you've learned something useful from my part. Now Frank will take over, and let's learn a few things from him.
Okay,
that's fantastic. Thanks, Stephen. So while Frank's just getting his screen up, as I'll just remind participants, if they do have any questions, please send them in so that we can respond. But also, please don't worry about trying to have to follow along with your computer now. This is being recorded, and you can watch it on demand. Fantastic, Frank. All over to you, and good evening.
Good evening, and thank you. Now, I'm going to be using Nspire to illustrate a coordinate geometry approach to inverse and composition of functions. So in the first problem, we're going to look at let P be a point on the graph of y equals f of x with coordinates xf, yf. The rule for f is given by simple linear function, 2x plus 3, defined over its maximal domain. Explore the locus of Q, which has the x and y coordinates reversed. So I'm going to use some geometry tools to explore this. So first of all, for this sort of work, I find it useful to have a grid. So control menu and hide show. Number 2, show aligned grid. Now I'm going to start with my point P. So geometry, menu geometry, which is 8, and points and lines, and a point on the curve. And you can see the little tool there showing that it's the point on tool. Escape that. Move this out of the way. Okay, I can label that, so just touch it, control menu, and label to, that's my point P. Now, the other thing I want to, actually, just so that I can keep track of that, I might just put in a text. All right, so I want to store this value as XF, so I can control menu, store number 5, and XF. And this one I can store as YF, so control menu, 5, and YF. Okay, now with my point Q, I want to reverse those coordinates. So I just put in a point Q, so geometry and points and lines, and this time it's just a point. I can put the point anywhere, and I'll label it. And I might actually change the appearance of that. So if you control menu and you go down to attributes, I might change that for it to look like that. You can also, of course, change the color. So control menu again, and I might go for green. Okay, and I want these coordinates. So you just touch the point, control menu, and number 7, coordinates and equations. So what I want to do is store the coordinates of Q so that they are the opposite to the coordinates of P. So I'll try this for a start, which isn't going to work, but we'll get around it. So I touch the point and go control menu and 6 variables and link to. Now I want to link that, the X coordinate of Q, I want to link to the Y coordinate of P. But it says I cannot link that twice. So the way you get around that is to insert a notes page where you can do interactive computation or dynamic computation. So control I or control doc, I'll add notes. And in the notes, I want to add a maths box. In a maths box, I can do dynamic computation. Now, if I go menu, insert, I can see maths box. But you'll notice that it's control M is the shortcut. So in practice, I always use control M rather than going through the menu. So what I want to do here is this point YF, the Y coordinate of the point P, I'll store that as the X coordinate of the point Q. And the X coordinate of the point X, I'll store as the Y coordinate of point Q. Okay, so we can see that I can now select those points. If I go back and do this variable, I can now link to XQ, which is the same as the Y coordinate here, and do the same for this one. So link to YQ. All right. Now, what I'm going to do, I could move this point P, but instead I'm going to do something a bit more interesting. I'm actually going to animate the point. Now, to animate a point, you touch the point and control menu and go down to attributes number 3, and down here you've got the animation. Now, 0 animation means that it's traveling at speed 0. You can choose an animation speed from 1 to 9, 9 being the fastest, 1 being the slowest. So we want to go slowly, so we'll choose 1. So you just press the 1 and enter, enter, and you get this little control, and you see that the point is animated. And something else I'm going to do, I'm going to put the midpoint of PQ in there. So menu, geometry, and construction, and midpoint, number 5. There we go. And that midpoint, I might make that look like a cross. So I can attributes and choose that. Okay, so the other thing I can do is I can leave a trace. So I can see that the point Q, and indeed the midpoint, is leaving a certain trajectory. Now I can leave a trace by going to the point that I want traced, control menu, and you'll see 9, geometry trace. And if I now animate the point P, I can see that Q leaves a trace. And what I like about this is that students can see that all we've done is reversed the X and Y coordinates. And from there, of course, students, this time I'll animate, I'll get the trace for this, the midpoint, and all the domain constraints that Stephen spoke about, I think can be investigated using this approach. So I'll try that again. Okay, and we can see the trace that's left by literally taking a pointwise approach. And if we're to do Control G or Tab, and actually I'll backspace and up arrow to get to relation, move this control out of the way. So as Stephen did, if X equals F1 of Y, and of course, because we had a linear function to start with, obviously the relation that we get is a functional relation, and likewise Y equals X. Okay, so that's just taking a pointwise approach. And once we've created a template like that, we can change that template and just input a different function. So, for example, in this case, it's essentially the same template that I've already created. I don't have to create it again. In fact, if you save the template into the My Widgets folder, then when you press Control I, one of the options that you've got is Widget, and you can just choose the template from the widget. That's another option. Okay, so this time I've got the parabola. I'll get the trace, and similar to what Stephen showed, we're going to get a relation which is not a functional relation in this case. And of course, just as Stephen did, we could restrict the domain in order to have a functional relation. Okay. Now, and the sort of questions, of course, Stephen's already had a look at as to if f of x equals 1 minus x, x minus 1, x plus 3, then f minus 1 exists to always, sometimes, or never. Of course, the answer is sometimes, depending on the domain. There are infinitely many functions with that rule. It depends on the domain as to whether f to the negative 1 of x exists. And what's the largest subset of that domain for which the function is 1 to 1, and looking at the turning point, it's from negative 1 to 5 on 2. So this file, already made up for you, is available for download after the webinar. And from doing this sort of work, you hope that students realise that for the inverse to exist, it must be 1 to 1, which has already been discussed, and of course the range of f to the negative 1 is the domain of f. And that becomes pretty clear just from that trace that the pointwise approach uses. Okay, now I want to move on to composition of functions. So a coordinate geometry approach once again, and this time I've got two functions. F of x is root x, and g of x defined over its entire domain, x squared plus 1. So what we're going to investigate is the function h of x, which is g of f of x. So we're going to use a coordinate geometry approach, and the template is set up very, very similar to the one we did, I did earlier in inverses. Now, one definition of function composition, which comes from Wikipedia, is function composition is the pointwise application of one function to the result of another to produce a third function. It's what Stephen was talking about as well earlier. And I guess it illustrates that a pointwise approach is quite appropriate. Now, this is basically, this diagram is showing much the same as what Stephen's diagram was showing with Venn diagrams. This is just using different notation. So if we consider points f, g, and h on the graphs of the function f, the function g, and the function h, then in g of f of x, what we're effectively doing is taking the y-coordinate of f and substituting it as the x-coordinate of the point G. Now the output, which is the y-coordinate, is then the y-coordinate of the composite function. Whereas you can see, even just from the notation, the x-coordinate of the composite function is just the x-coordinate of the original, what I'll call the inside function f of x. So when we take a pointwise approach, now I'm not going to do this from scratch because we're going to run out of time having started late. So this is what I prepared earlier. So I've set up the template similar to the inverse one, except this time I've got the y value, the y coordinate of f, I've stored as the x coordinate of g, the x coordinate of f as the x coordinate of the composite function, and the y coordinate of g as the y coordinate of h. Now, if we ask the calculator to evaluate, having defined f of x and g of x, we ask it to evaluate g of f of x, it gives us a rule, but it tells us nothing about the domain other than a warning. It does give us a warning that the domain could be something other than the maximal domain, I guess. Okay, so going back here, having basically adjusted the coordinates appropriately, I'll get this to leave a trace, so point H, I'll go Control Menu 9, Geometry Trace, and when I set point F moving, we see that we get that as the result. Okay, so if we do Control G and we input G of f of x, whoops, we see that, in fact, the calculator has graphed the correct function with the correct domain. But I think the point-wise approach, I guess, is showing what's happening on a point-by-point basis. All right, so in the next one, what we're hoping that, some conclusions that we're hoping students see from this is that if H is G of f of x, then it is defined if and only if the range of f, the range of the inside function, has to fit inside the domain of G has to be larger than the range of f, since you're replacing f of x with your original x values of G. And I think that Stephen covered that quite well, very well, in fact. And of course, the domain of the composite function is the domain of f. It's the domain of the inside function. I think they're the two things that I'm hoping that students would appreciate from doing this as a point-wise approach. Okay, so problem 2, this time I've got essentially the same, except I've changed the function. So the reason I've included this is just to show that once you set up the template, all you need to do is change the one or both equations, and it's all set to go. So, by the way, if you control menu somewhere where it's empty and you hit the erase trace, the trace gets erased. Now, this is obvious. I was playing with this before the session, and that's why it's there. So once again, if you just touch H, control menu, and graph trace, and you see the composite, or a point-wise locus forming with the composite function. Okay.
Frank?
Yep.
Somebody just asked the question, is there much of a difference between using the store functionality or the assign function when you're setting variables?
Absolutely none. They're identical.
Yeah.
I think the only reason I probably use store in that case is I think the arrow, it just matches the diagram I had, where I had arrows pointing from one thing to the other. That's the only reason I used the store. So store, assign, define are identical. Yeah.
But it's more just the syntax, isn't it? Because they're just perhaps the opposite way around. So like you said, it just follows whatever you're using a bit clearer.
That's right. Yes. Yes. It's just that normally I use the assign. The only reason I used it there was because the arrow was consistent with the diagram that I'd used.
Yeah. Great. And that point-wise is a very nice function as well, isn't it? Because it really, like you said, it does it point by point. You really can clearly see what's evolving and predicting where it's going to go next.
That's right. That's right. So that approach, or the approach that Stephen was showing, where you actually grab the end and drag it along, I think works much better than the approach where the calculator just shows you the answer by magic.
Yes. Great. Thank you.
Okay. So in this case, we've got these two functions again, except this time, instead of G of f of x, it's f of g of x that we're going to investigate. So the template is exactly the same, except all I need to do is just reverse the f and the g, and that's basically it. And you can ask questions like the largest possible subset of R, so that the function, the composite function is defined. Okay, so once again, the diagram is the same as before, except you just interchange the F and the G. So this is one I prepared earlier, and once again, this time it's the point K, so I'll leave a trace with the point K and animate. This time it's point G I'm animating. And we can see that the point, it can only move, it's interesting that the point only moves from -2 to +2. It doesn't let you go anywhere else because of the way that I've constrained these variables. In fact, here I've used the assign here just to show that it makes absolutely no difference. Okay, so that answers the question that the largest possible domain of g of x for which the composite function exists, or it's defined, is from -2 to +2, and that looks as though it might be a semicircle, and in fact, if we evaluate f of g of x, that's exactly what we get, a semicircle of radius 2. And once again, if we let's get rid of this. What I want to do, sorry. Okay, so we get the semicircle. What we want to do is some conclusions, basically the opposite before, that this time it's the range of G has to be a subset or equal to the domain of F, since the G of X has to fit in as the X values for F, and the domain of the composite function is the domain of the inside function, in this case is G of X. And the last thing, this is something you can investigate yourselves by downloading the file. You can actually do the same thing, finding the composite function where the two functions are inverses of each other. And the way I set that up is by one function being f of x, the other one just being asking for zeros of x minus f of y and storing that into g of x. And that guarantees that you get the inverse function. And if we get the geometry trace, as you'd expect, the composite function, the composition of a function and its inverse function is the line y equals x. And I think that's it. I think we're out of time. So thank you very much for listening.